Yeah, sure. I get that. That's the record.
All right, I guess we might as well start. So can you start it?
Yes, I already started. Yeah.
Oh, you already started. Okay, well, this is the pre-Thanksgiving lecture. Let's see, I owe some of you a candy who asked questions when I was out of candy. Does anybody remember who it was? You must have asked one. Okay. All right, well, let me start by summarizing some of what we've learned and some of what's important. First of all, we're talking about second-order ordinary differential equations. We can write them in Sturm-Liouville form like this. Rho is a weight function, and this function rho often occurs from the transformation that takes the second-order ordinary differential equation into Sturm-Liouville form. We then normalize the eigenfunctions with respect to the weight function rho that arises here. And the thing that's really important mathematically and in quantum mechanics, quantum field theory and so forth, is that these eigenfunctions are not only orthogonal, but they're complete, or orthonormal, but they're complete in the sense that they can represent any function that's square integrable on the interval that we're talking about with weight function rho. And the best way to think about these integration is Lebesgue integration, and since we're not taught that in school, I just gave you a brief description of it. But the Lebesgue approach to integration makes many of the theorems that are hard and have lots of funny conditions much simpler and more general. In any event, the important thing is that you can expand any square integrable function in terms of the eigenfunctions with coefficients, and the orthonormality of the eigenfunctions implies that the coefficients are given by this formula, and what you have here is convergence in the mean. So this is convergence in the mean. And there's an interesting consequence of all these formulas. Namely, we can rewrite this formula as, now what's the best way to rewrite it? Well, I'll just rewrite, yeah, I think this is the best way to rewrite it. So I'm using the formula for the AIs, which are these, and over here I'm going to change x to y. So what we have then is f of y, sum I equals 1 to infinity, ui of y, ui of x, rho of y, dy. And now if you look at this equation, f of x equals this, you see that this thing here is a delta function. That is to say, delta of x minus y, and of course it's really a delta distribution. Delta of x minus y is the sum, I equals 1 to infinity, of ui of y, ui of x, rho of y. So that's by the way, the last two people who just came in, I need to talk with you after class, okay, for 5 minutes or so. So what we have here is a representation of Dirac's delta function in terms of the eigenfunctions and the wave function. And it's extremely general. And I, in fact, did a computer test of this relation, which is figure 6.2 in the book. And those of you who don't have the book, this is what it looks like. These are 3 delta functions. And what I did there was, first of all, this thing, since it represents a delta function, the formula doesn't care whether rho is evaluated at y or x, because x has to be equal to y. And so you can rewrite this as rho of y to the alpha times rho of x to the 1 minus alpha. Anyway, so that's what I actually did. In other words, you can write this delta of x minus y as, wow, what is that, a typo or what? Oh, I see. It's that 4, all right, let me back up and say what the example is. The example is minus x u prime prime plus n squared u over x equals lambda x u. So rho of x is just x. This is Bessel's equation. And those are the eigen functions. The eigenvalues are lambda is, I'm writing it here, as z squared sub n k. N is this parameter that specifies the differential equation. K is the integer that specifies the eigenvalue. And so what I did was I considered the case x to the alpha, y to the 1 minus alpha, a sum u k n, n meaning the differential equation specified by n, okay, so I computed that where here for n equals 0, and for n equals 0, this thing came out to be delta of x minus y equals 2x to the alpha, y to the 1 minus alpha. Remember, x and y are representing rho of x and rho of y, because rho is just x for Bessel's equation. Sum on k from 1 to infinity, j0 of z0 comma k x, j0 of z0 comma k y, divided by j1 squared of z0k. So those are, the reason why we have this is for normalization. Anyway, I plotted it for 3 cases. Alpha equals 0, and y equal to 1/3, alpha equals 1/2, y equal to 1/2, and alpha equal to 2/3, and I'm sorry, alpha equal to 1, and y equal to 2/3. And I was really amazed at how it worked out. The plot looks like this: minus 200, 0, 1,000. And I plotted the sum of these things for these 3 cases, just to show you that the alphabet can be varied. And what happens is that at 1/3, it goes up to 1,000. At 1/2, it goes up to 1,000. At 2/3, it goes up to 1,000. And then there's some jiggering here, which this was the sum where I did not use infinity. I used just 1,000. And anyway, those of you who have the text can look at it. All right, so that's the completeness. And is there any restriction here on the type of Sturm-Liouville equations that are systems that give you this? Well, the restriction is that the eigenvalues have to go to infinity. But this is a generic feature of Sturm-Liouville systems. And in order to see that, let me just pop back here in order to see that, let's remember what I think we saw last time, which was that the eigenvalues are the things that minimize the energy function divided by the normalization function. And that's an integral going to be p u prime squared plus q u squared dx over ab. Wait, there should be a row there. Or is there a row? Maybe there isn't any row. Let's look at the differential equation. Yeah, I guess if you have this, you don't need the row. Down here you have an integral u squared rho dx. And so what we, I think, showed last time was that if you're looking at functions u that satisfy the boundary conditions, Neumann or Dirichlet boundary conditions, and the differential equation, then the The function that minimizes this ratio is the eigenfunction for the lowest eigenvalue. Then if you look at the function that minimizes this ratio and is orthogonal to the lowest, to the first eigenfunction, then you get, for this ratio, the second eigenvalue, and so forth. And so, in general, lambda sub n is the eigenfunction that minimizes this ratio and is orthogonal to the first n minus 1 eigenfunctions. Now, why do the eigenvalues go to infinity? Well, it's kind of obvious. It's because what you have here is a derivative squared. And so if, let us suppose that this is an eigenfunction, well, you can do something like that with arbitrary high frequencies, and you make this arbitrarily big. So this ratio can get arbitrarily big. And that's basically why the eigenvalues go to infinity.
So what do you mean? Sorry, what do you mean by do that? Like whatever you drew this quickly. Like what do you? Oh yeah, but what are you doing? Yeah.
All right.
What are you doing to do that?
All right. He just wants another candy. Okay. In particular, I was considering the simplest of these eigenfunction equation, just the equation that defines the sine or the cosine. And I was setting u sub omega of x equal to u of x, whatever that may be, 1 plus 0.2 sine omega x. And I was letting the zigzag curve is omega equal to 100. Okay. And what you can do is you could do something like this. 1 over omega, sine of omega, let omega go to infinity. And the zigs are arbitrarily rapid but slow. Actually, what one might do is make this square root of omega. Then when you differentiate, you get a square root of omega, and the square of that would make this thing diverge. So it's easy to show that one way or another that these are, that the eigenvalues go to infinity. Let me now just sketch the proof. I'm not going to go through the whole proof of this. But the way one does it is one defines a new functional of two functions. An integral a to b, e of x, f prime of x, g prime of x, plus q of x, f of x, g of x, dx. And similarly, a norm, which, well, an n function is not really a norm, rho fg dx. And now what you can show, and by integrating by parts and using the boundary conditions, you can show that EFG is equal to the integral a to b f, the differential operator L, which gives you this. Plus the boundary term P F G prime A B, and this of course is 0 because we're choosing functions, I'm choosing functions in the domain. So for functions in the domain, all we have is that. And so now I want to write an arbitrary function of the domain as a sum ck uk of x, k equals 1 to n, say. And the CK coefficients are, let me just save time by saying that it's NF UK, and I hesitate to pronounce that. Okay, now, what's the remainder? In other words, what's the error here? The remainder is f of x minus the sum k plus 1 to n of ck uk of x. All right. And this n of the remainder Rn with uk is 0 for k equals 1 up to n, because just of the orthogonality relations. That is to say, we pick these to approximate f as well as possible on the first n. So this Rn is orthogonal to the lower eigenfunctions. It follows, therefore, that the next eigenfunction, un plus 1, will minimize the ratio u, or let us just say an arbitrary function, e phi phi over n phi phi. It will minimize that. And if we call this thing R, capital R of phi, then R, of course, of u n plus 1 will be lambda n plus 1. It will be the n plus first eigenvalue. And what follows then is that since this remainder is orthogonal to all the lower, is orthogonal to the first n eigenfunctions, it's a linear combination of the higher eigenfunctions, and consequently, this lambda n plus 1, or let us put it this way, lambda n plus 1 is less than or equal to the R function for the remainder, because the only way that the remainder, the lowest value of the R ratio for the remainder would be if the remainder were equal to un plus 1. And, well, consequently, we're done. Because you see, this is E of Rn over lambda n plus 1. And this, of course, is effectively the norm of the remainder, norm in the sense of the integral of the remainder squared rho dx. So what we've got here is that the norm of the remainder squared, which is to say R of the remainder. Oh, all right, this equation is wrong. This should be that this is this is an R. R sub n is that, and let's start a new equation here. Lambda n plus 1 is less than or equal to the remainder thing. And consequently, this, which is the same thing as integral rho Rn squared dx, that's this, is therefore less than or equal to E of Rn over lambda n plus 1. Now, did I, hold on a second, I screwed this thing up. This is the punchline and I screwed it up. This is n. Okay. So the ratio for Rn is the ratio of these two things. The lowest value of this ratio is when R sub n is just equal to U. And so if Rn were equal to Un plus 1, that would minimize this ratio. So in general, for arbitrary Rn, it's greater than that. So then we have this inequality, namely that this thing, multiplying both sides by this and dividing both sides by lambda, we get this equation that the norm of the remainder is less than the energy term of the remainder divided by lambda n plus 1. And consequently, what one can show, the next step, which is, I'm not going to prove, I'm just going to indicate that it's plausible. Namely, we know that the lambdas go to infinity as n goes to infinity. If we can prove that this term is bounded, then it follows that the remainder goes to 0. The remainder goes to 0, that means that this function approaches f of x in the mean. And so that means that the eigenfunctions can converge in the mean to any function in the domain of the Sturm-Liouville system. And the next step to getting completeness in L2 of AB is to say that the domain is dense in L2. Well, the domain the domain is basically all continuous twice differentiable functions that satisfy the boundary conditions. But the boundary conditions really don't matter when we're talking about convergence in the mean in the sense of Lebesgue, because after all, the points at the boundary at AB are measure zeros, so one can blow them off. Okay, so that's basically the argument there. If you want to see it in more detail, you can look in the book. All right, let me now skip on to some inequalities of Bessel and Schwarz. This is an obvious this is obviously greater than or equal to 0, and that implies Bessel's inequality, which is the integral a to b rho f squared dx is greater than or equal to the sum k equals 1 to infinity of ak squared. I'm doing this for real, assuming everything's real, which for practical purposes is the case. Let me also state a version of Schwarz's inequality, ab rho f squared dx times ab rho g squared dx greater than or equal to integral ab rho g bar f dx. I guess it's worth doing them in for complex functions. So that's the that's the value squared. So that's a Schwarz inequality. All right, now I want to say a few things about Green's functions. After saying a few things about Green's functions, I want to finish chapter 6 and start. I'm going to skip chapter 7 on integral equations. I'm going to just jump to Legendre functions.
Do we not have time for integral?
What's that?
Do we not have time for the integral equations chapter?
I'm going to skip integral equations.
Is there not enough time? Yeah, could we go back at the end of the class if we have time? Or
Yeah, well, we could do it next semester if you want, in 467.
wait, that's being offered next semester?
Yeah, well, 467, yeah.
Oh,
It's the second half of the book.
oh, okay.
But because 467 is not a core course, I don't have to give exams. But I will give candy. Okay, so physics has lots of equations like this. Some differential operator operating on some function g of x gives you delta of x. These things are called Green's functions. And an important example is minus divergence gradient g of x vector equals three-dimensional delta function of x. This, of course, is used to give you the electrostatic potential in electrostatics in terms of an arbitrary charge distribution. The formula for this is pretty obvious, namely g of x is just an integral e to the I k dot x over k vector squared 2 pi cubed e cubed x. And the reason for that is that when you hit this first with the gradient, you pull down an ik, you hit it then with the divergence, you get another ik, and that gives you minus k squared. The k squareds cancel, and so what's left is minus the delta function, and that cancels the minus sign there. The delta function in general being delta cubed, or if you want, delta n of x, n vector, is an integral e to the I k dot x dnk over k nkn, an nk vector, wait, not dotted n, squared, but it's an n vector, 2 pi to the n. So this is the formula for the delta function in n dimensions. If you do this integral, what you find, as you must know, is that this is 1 over 4 pi absolute value of x. And this is the thing that gives you the Coulomb potential. If you modify that equation a little bit, you then have 2 of Helmholtz's equation. Let me save chalk by saying that divergence of gradient is triangular, okay? Three-dimensional Laplacian. Minus Laplacian minus m squared g Helmholtz at x. Okay, the answer is g Helmholtz of x is e to the I m r over 4 pi r. So r is the length of x. Another Helmholtz equation, and I guess I called it mh of x, delta cubed of x, of course. The answer here is the g mh of x, I guess m means minus, is e to the minus mr over 4 pi r. This is the Yukawa potential, which describes the interaction of nucleons at low energy. In fact, one of the many mysteries of physics, we pretend that we know it all, but actually we don't. And in the theory of the strong interactions, there's the mystery of why quarks are confined, why gluons are confined, which is an even bigger mystery. And then finally, if the real theory is a gauge theory of quarks interacting with massless gluons, how come nuclear physics is described by nucleons interacting with pions that weigh 135, 140 MeV? So those are some of the confusing things. This particular Green's function is, of course, very important, and let me just say something about what it is. Namely, it is a sum, L equals 0 to infinity, a sum M equals minus L to L, 1 over 2L plus 1. I call this the Sturm-Liouville extension. R lesser to the L over R greater to the L plus 1, YLM is theta in P, YLM star of theta prime and P prime. So, theta and phi are the polar coordinates, the angular polar coordinates of x, and theta prime, p prime, angular polar coordinates of x prime. R lesser is the smaller of the absolute value of r. R greater is the larger of the absolute values of x and x prime vectors. Okay, let's skip through that. All right, let's skip through a little bit more. Okay, how will I do it? All right, here's a formula for Green's function that's related to the stuff about completeness over there. Sum on k from 1 to infinity, uk of x, uk of y, over lambda k, the kth eigenvalue. Why does this work? Well, L on g of x minus y will be a sum L on uk of x, uk of y, over lambda k. And what does that do? Well, the equation, of course, is LUK is equal to lambda rho UK. So we can replace lambda UK by a sum, we can replace L on UK by lambda K rho UK. And then what we get is rho of X, UK of X, UK of Y. And we've seen that this is delta of x minus y. So another formula for the Green's function is this. Okay. And now that I think about it, I really ought to write a computer program to do the Bessel function thing with these eigenvalues. Yeah, this form instead of the other one.
What the Green's function?
What?
That's a formula for the Green's function.
For the Green's function, it's very general.
Okay.
This is a formula for the Green's function of the differential operator of which these are eigenfunctions. Rho is the wave function, lambda the eigenvalue.
How we find the UK corresponding
How to find what?
UK, the eigen function.
How do you find it?
How do you find the eigenfunction?
All of them? Yeah.
Find? How do you find it?
Yeah.
Well, in general, it's difficult to find eigenfunctions. I mean, there's nothing trivial about that, right? All right, but I owe you guys some candy. There were 2 questions here, right? One for you. You asked a question? Let me grab a water here. Okay, so there is another formula for Green's functions, and so I'm just going to write this down really quickly. Namely, g of x and y It's the heaviside function x minus y, u
For the
of
Lagrange
y,
function of the
v of x, plus theta of y minus
the general
x,
formula for any Lagrange function.
u of x, v of y, divided by something related to the Wronskian, namely the minus sign and the Wronskian at some x0 and p of x0, where p is the p function in the self-adjoint form of the differential operator. Okay, so that's worked out in the text. Going through all the details is a little bit time consuming, so I'm going to skip that. Okay, let me now switch to something that I did in the problem session a while ago, but some of you may not have seen it. And when I did it in the problem session, I didn't emphasize, I didn't give you enough of an example of something. So first of all, what's an autonomous system of first order differential equations? Is f1, x1, xn, dot, 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 x dot n equals fn, x1, xn. So this is called an autonomous. Well, these dots are a little bit dangerous. I'll put them over here. Oh, that's dangerous too. All right, so just a sequence of n first order differential equations. It's said to be autonomous. I don't know why I'm even using this word, because it doesn't mean anything more than time independent. I can't spell it damn. Anyway, x1 dot through xn dot is that. There's no explicit t on the right-hand side, time independent. However, these are extremely general. Suppose we did have time dependence. Well, then we would have a t here. How do we make that time independent? We just have x dot n plus 1 equals 1. And we say here that x n plus 1 is equal to t, x n plus 1 dot is 1, that's this equation. And we just rebaptize t n plus 1 here. And we've got xn plus 1, xn plus 1, and this thing is called 1 is equal to f n plus 1 of x1 to xn plus 1. So you can convert any time-dependent system into a time-independent system at the drop of a hat. Moreover, if you have a nonlinear high-order differential equation, you can still throw it into this form. So this is extremely general, these autonomous systems. So let me show you this example. Y triple dot. All right, I'm just going to turn it off like that. Yes, okay. Okay, y triple dot equals minus y double dot squared plus y dot cubed minus y squared. So this is a third order ordinary nonlinear differential equation. Okay. Doesn't look at all like an autonomous system of equations, but by changing the names of things, something the Republicans are doing with the tax cut bill. Let x1 equal to y triple dot. Let x2 equal to y dot. Let x3 equal to y. Then we can rewrite this equation as an autonomous system. x1 dot, well actually this thing was autonomous to start with. So forget about it being about autonomy and non-autonomy. It's then x1 dot is minus x1 squared plus x2 cubed minus x3 squared. x2 dot equals x1, x3 dot equals x2. So these are first order autonomous systems of different.
I think X1 should just be Y double dot.
All right, let's see. X1 should be Y double dot, yes. All right, you get 2 candies. Hold on. All right, so now there are 2 reasons for mentioning this. One is that once you have a system of equations once you have an autonomous system of first order ordinary differential equations, there are computer programs that will integrate it for you. You just give the initial conditions, and it's pretty amazing what they can do. Computers can do these days. Okay, so let's see. We've got all right, I think I can finish 6 and start 8 in a little bit of time. So let me do the principle of least action in field theory. This is something that's important in so I'm basically setting C equal to 1 because I don't want to have extra C's. So d4th x is, well, you don't even need C equal to 1 here. d4th x is just dt, dx, dy, dz. And L is the Lagrange or Lagrange density or the action density. This is the action. Phi is any function. A field is nothing more than a function of space-time. So it's a jargon term that probably. All right. Anyway, what's the first order change in S? Well, it's obviously partial L, partial phi, change in phi, plus partial L, partial the 8th derivative of phi, change in the 8th derivative of phi. By 8th derivative, I mean derivative at the time, to t, x, y, or z. And the change in the 8th derivative is the same thing as the 8th derivative in the change. And so I can rewrite this as dA of partial phi. And now we can integrate by parts, and what we have then is partial L partial phi minus dA of partial L partial dA phi, all that times delta phi d4th x. Okay, if we plus a surface term. I'm just going to write it like this. But if we require that S be, that the change in S be 0 to first order in the change in phi, and that the change in phi, whenever the change in phi vanishes on the boundary, then the boundary term isn't there. And in that case, we get Lagrange's equations, which are dA of partial L partial dA of phi is equal to partial L partial phi. If you have a theory with several fields, you just add a subscript here. And so that's a theory of an arbitrary number of fields, scalar fields. Actually, they can. This whole business here works for any kind of scalar, vector, tensor, whatever fields, because the same argument goes through. Things get a little stickier if you have spin 1/2 fields. And the reason is that we typically have to represent them by quantities that anti-commute, so this gets a little bit different. Okay, let's now do the conserved quantities that are related to symmetries, and this is something that a woman somewhere in Scandinavia, I think, Emmy Notha, was the first to explain. So suppose you have a symmetry, and the symmetry is a symmetry of the action density L. So you're saying 0 is dl, and what is this dl? Well, it's the sum over the various fields, the change of L d phi I, with respect to phi I, the change in phi I, plus partial L partial dA phi I, the change in phi I, or the change in the derivative, that's the same thing as the derivative of change. So that's what we're assuming. Now, so suppose you have a symmetry, then use Lagrange's equations, and then this thing, partial L partial phi I, is partial A of partial L partial of the 8th derivative of phi I. So the symmetry is rewritten as a sum. This thing becomes dA of partial L partial dA phi I, change in phi I, plus partial L partial dA phi I, dA change in phi I. Now you see this is a total derivative. This is just dA of a sum on I of partial L partial dA phi I times change in phi I. So what we have then is we have a conserved current, JA, and JA is the sum on I, partial L, partial dA phi I, times the change in phi I. Now, let me explain what this is. This thing is conserved, that is to say, 0 is dA JA. This is conservation. And what that means is that the divergence of the current is the minus the time derivative plus the time derivative, one or the other. So that if you have the thing change, the density J0 changing in a certain region, it has to be due to the flow of stuff in or out of that region. This part here is the symmetry part. In other words, it's a change in the I field that doesn't change the action density. What is the thing that's conserved? Well, the thing that's conserved is the integral of J0 over space. J0 then is the sum on I, partial L, partial, A is 0. This is time derivative. And you remember that the momentum conjugate to a field is the derivative of the action density with respect to the time derivative of the field. you remember, or you will remember it after you encounter that in another course, which I hope you will. So this thing is actually pi I times the change in the field due to the symmetry. That's what's conserved, a d cubed x. So, conjugate momentum, momentum conjugate to the I field, change in the I field that doesn't change the action density, integrated over space, that's the thing that's conserved. An example, I don't think we can, I don't want to do this in detail, but you can, I tell you what, I think this is not in the first edition of the book. I'll maybe put this little section on the class webpage in case you want to see it. It's a derivation of, what's a particular symmetry here? The Lagrangian is unchanged if so delta L is 0 if delta L is due to the fields, the I field, the change in the I field at x is phi I of x plus a being a 4 vector, because x is txyz, minus phi I of x. And so that's a translation. And the thing that's conserved then is the energy momentum tensor, TBA, which is the sum over I, partial L, partial dB of phi I, partial phi I, partial XA, minus delta BA L. So that's the energy momentum tensor.
I have a question over something you did before. So with this, you're talking about this like conserved current, and it seems like you have like you have this JA, and it seems like you would have a JA for every different like coordinate that you have for every different A, like 0, 1, 2, 3, I guess.
The thing that's conserved is the 4 vector JA. Conserved in this sense, and in that the space integral of the time component of J is constant, or to put it differently, the integral, the space integral of J0 over some volume either has no time dependence, or the time dependence is equal to the current J3 coming in or going out of the volume. Okay, in other words, charge is conserved. The charge inside this circle here, say, is conserved. What that means is that either the charge inside doesn't change, or it changes because the charge comes in or goes out.
Okay. So so you're kind of so it's like this like you have this like gradient over JA equal to 0. So that's like a 4-dimensional gradient. One at a time through the space.
All right. Yes. 0 equals J0 dot. So there are 2 dots on J. One because it's a J, and the other because it's a time derivative. And this dot is because it's a J, not because it's a time derivative. I guess I should use capital J's for conserved current. Okay.
Yeah, I don't know. Should there be a minus sign?
Huh?
Should there be a minus sign on on either the time part?
Oh,
or the
no,
space part?
no. No, that's just J equals 0, 1, 2, 3. You sum them up.
Sure. And so then you're getting that Q is a conserved quantity because you're just rearranging the equation and integrating?
Give me that again. What?
And so then you're getting that this Q is the conserved quantity because you're just rearranging this equation, getting J0 dot on one side and then integrating it? Or what exactly?
Okay. All right, here. What's Q dot? Q dot is the integral, let's use capital J, 0 dot dq dex. That's equal to minus the divergence of J dq dex.
Yeah.
That's equal to minus the integral of J dot ds over a surface that includes the volume. So this is a volume V, and this is over a surface that is the skin of the volume.
And
So the time derivative is the stuff coming in or going out or whatever.
And so that's all equal to 0?
Huh?
So then that would all be equal to 0 then, or no?
No, this can be non-zero. For example, the charge in your body changes if an electron hits your shoulder.
So is it a conservative quantity?
Yeah, so it's, yeah, that's...
So the change, the time derivative of the charge is the current flowing in or out.
Okay, so is Q a conserved quantity?
That's what a conserved quantity is, yes. The
Oh.
charge is the conserved quantity in this case. And in physics, one uses generically charge for
Yeah.
all kinds of
I
things
think
that are
what he's
conserved.
saying is okay, so the idea is conserved doesn't necessarily mean non-changing in time.
It means that,
It
well,
means there's a quantity that's
here's
changing
the
in time,
thing. I mean,
some load is compensating for
if
that.
the charge on your body changes only because electrons come in and out, that means that,
The charge-
and if that's true for everybody, including
Okay,
chairs
so if you
and
make
tables and so forth,
Okay, so if you make your boundary like the boundary of the entire universe, then it's equal to 0.
all right. What I used to say years ago was, that means that the charge is conserved because we don't have enough funding to change to have a current at infinity in the experiment. But that's sort of
Okay.
stupid. It just means that if something changes, it's because the current flows in.
Okay,
That's all.
sure, I see.
Okay, here, I'll take that to be one long question.
Yeah, sure. Oh.
All right, there's a little, oh, thanks. There's a little more about,
What?
all right, let me just give it,
Like, do you have like an extra derivative here, or it's a partial? Do you have, like,
this
an
is a
extra-
B.
No, but do you have like an extra partial of B?
No. It's the partial of the action density with respect to the B
And what is
derivative of the I
What
field.
is the previous symbol?
This is
that?
the,
Partial.
this goes with that.
Oh, okay.
Here. Great catch. Okay, let me just give an example of some differential equations that are important in astronomy and cosmology. If you have a homogeneous isotropic universe, in other words, our universe on a big enough scale, very big scale, you then basically are describing everything in terms of a scale factor, almost everything. And you have the equations then that are called the Friedmann equations. 4 pi Newton's constant over 3, a mass density, pressure, c squared. That's one equation. The other equation is even simpler, but more nonlinear. A dot over a squared is 8 pi g over 3 rho minus c squared k over a squared. Okay, I'm just going to write them down. You can look in the book for a little more detail about them. There are other. Okay, let me just Is this all an example? Yeah. There's something about solitons that ends the chapter. If you want to hear about solitons, ask me on Wednesday in the Wednesday class. Okay, now let's try to do something about chapter 8. So this is a huge change of pace, but it's essentially, in some ways, an application of what we've already learned. Suppose we want to expand a function about the origin. Well, we can do such an expansion. Normally, if the function is suitably differentiable, this is the nth derivative over n factorial times x to the n. And so what that tells us is that these monomials, x to the n, are complete. So the x to the n are complete, at least for expanding functions near the origin. So what the Legendre polynomials are is an application of this to the interval -1 to 1, which is neighborhood of the origin. And we make two requirements. One is that the inner product of two Legendre polynomials, defined as an integral of one times the other, should be 0. That is to say, the Legendre polynomials should be orthogonal. So these are orthogonal polynomials. There's a whole area of mathematics of orthogonal polynomials. These are probably the simplest orthogonal polynomials. And one way to make them orthogonal is to say that Pn of x, x to the m dx, is 0 if m is less than n. So this implies that. And to make them unique, we impose a normalization condition. Pn of 1 is 1. So that defines the Legendre polynomial. And so what you can do is you can say, well, Pn of 1 of x is then a 0 plus a 1x plus dot 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 plus an x to the n. So it turns out then that these requirements imply that the nth Legendre polynomial is an nth order Legendre polynomial, and that the sum, when you set x equal to 1, Pn of x, Pn of 1 has to be 1. The sum of the AIs has to be unity. Rodrigues invented a nice formula, which I alluded to in the complex variable chapter, for the Legendre polynomial, namely Pn of x is 1 over 2 to the n, n factorial, nth derivative with respect to x of x squared minus 1 to the n. Now, you can work out what that is by using Liveness Rule, which chapter 4, equation 49. And what you find is that this Liveness Rule gives you 1 over 2 to the n, sum on k from 0 to n, the binomial coefficient nk squared, x minus 1 to the n minus k, x plus 1 to the k. Okay, that's a formula for that, and you can see by substituting x equal to 1 that this, in fact, does give you unity at x equals 1. Anyway, in the text there you see that this automatically, well, it's actually kind of interesting why this is true. The integral, remember, one of the defining features of the Legendre polynomials is the nth Legendre polynomial is orthogonal to all these monomials for m less than n. So let's check that Rodrigues got it right. Well, you integrate, this has an nth derivative with respect to x. You integrate by parts n terms. All the boundary terms vanish at the endpoints because x squared minus 1 is 0 at x equal to minus 1 and x equals plus 1. So this then turns out to be minus 1 to the n from integrating by parts, 2 to the n, n factorial from Rodrigues' formula, integral minus 1 to 1, x squared minus 1, the nth derivative of x to the m, dx. Well, if m is less than n, this is 0. And so indeed this is 0 for m less than n. So Rodrigues' formula satisfies the two conditions for a Legendre polynomial, one being that they're orthogonal to these monomials for m less than n, and secondly, that Pn of 1 is 1. There's also a generating function for the Legendre polynomials. Well, before doing that, let me just say that there's a nice integral formula these polynomials are orthogonal, and one can show they're orthogonal by using Rodrigues' formula. A generating function for them is this. G of t and x is 1 over the square root of 1 minus 2xt plus t squared. By generating function, I mean that this is a sum n equals 0 to infinity. And let me just make sure that everything here is, yes, t to the n Pn of x. So in other words, this rather simple function, when you expand it as a power series in t, has coefficients that are the Legendre polynomials. And what you've got obviously here is that p sub n of x is the nth derivative of 1 minus 2xt plus t squared to the minus a half at t equals 0. And you can also show that the integral g of t and x, g of v and x dx, so this is an integral dx over those two square roots, g of tx, g of vx. This integral is one you can do. 1 over square root of tv log 1 plus square root of tv 1 minus square root of tv. So, oh, and then we can expand this. The expansion of the log there is that this thing is a sum k equals 0 to infinity 2 over 2k plus 1 tv to the k. So now we've got that this, which is integral sum Pn of x t to the n Pm of x v to the m dx, this sum is equal to that. You equate powers of t and v, and you get this relation. And you can also check that the p's defined by this satisfy the boundary condition. Pn of 1 is 1. All right, I think we can stop there and any questions?